Okay. So last week in my class, I just mentioned that we are going the topic of our discussion for this semester. That will be liquids and gases. Gases. So we are going to take up the gases first. So when we think of gases, so this is a state of matter where the particles of the gas sample are having a very relatively high kinetic energy, is it not, compared to liquids and solids, because they move quickly through random motions everywhere. So you can have the first property of a gas is its diffusion, right? So they travel long distances if allowed. So that means they have a lot of kinetic energy. So straightforward, how to know the kinetic energy of a particle using our famous kinetic energy equation. Kinetic energy is equal to half mv square. So as evident from this equation, the kinetic energy is dependent on two properties of a gas molecule or any particle as such, not just gas, any moving body. M is the mass of that body and V is the velocity of that body. So they have direct proportionality. Now, if we have applied this kinetic energy equation and I have to calculate the kinetic energy of two different samples of gases. So how do we do this? So for example, I am taking oxygen and hydrogen. Why? Because there are two samples of gases. Smaller molar mass and mass. See, what is m is the mass of the particle. Now, if kinetic energy as, and this is equation for any moving particle which has come out from the Newton mechanics, classical mechanics, Newtonian mechanics. That's the equation. Half is equal to mv square, mass of the particle into velocity. Now, if we have two samples of gas molecules or two different gas molecules, oxygen, example, and hydrogen in the same flask and kept at same temperature, which one would you expect to have a higher average velocity? See, now we start looking into matters not from the angle of energy, okay? Because for our discussion, energy is not a very focused parameter. Rather, we will think about velocities, okay? Velocities. So if I have hydrogen and oxygen, both are enclosed in the same flask, which one would we expect to have higher velocity, higher speed? Simply, okay, let me put it as speed. Which one do you expect to have higher speed? Naturally hydrogen, right? Because of its smaller size compared to oxygen, much smaller compared to oxygen. So definitely hydrogen molecules would have a higher average velocity as they move. So we have one direct conclusion we have made. What is that? When we are comparing gases like oxygen, hydrogen, nitrogen, argon, helium, such gases, and predicting their relative velocities, straightforward we can tell this uh, conclusion. What is that? Smaller the molecule, higher is its speed. Fine. Smaller the molecule, higher is its speed. Therefore, we have this conclusion. But our topic of discussion is not concerned to is not concerned too much with relative distributions, like I'm comparing oxygen, nitrogen, helium, argon, not such things. Rather, we will ask somewhat a peculiar question, but a very important question. What is that? Yeah, let me ask the question later. Anyways, we will visualize how the gas molecules move inside a container. So you can see those dots represented by each molecules. Please stop your videos, all of you. I don't know why you. Uh, okay. So now, yes, you can see oxygen molecules, hydrogen molecules separately, or a few molecules, different colors. What is this cartoon telling us? That the molecules are under constant motion. One. Second, while they move, during their motion, what happens? Collision happens. So collision is a common phenomenon in sample of gas enclosed in a cylinder or enclosed in a container. They collide amongst themselves as well as they collide to the container's walls. Because of these collisions, what happens? The question, very important question. Because of this collision, what happens? Because of this collision, we have uh, something called distribution of energies. So what do we mean by this? So now let us think that two molecules are colliding, and after collision, they move, maybe in a different direction than the previous. They can deviate from their path and move. So when they happen, now let us assume that both the molecules were carrying equal energy. Now the molecule A and molecule B. And don't think this molecule A and B are from different gases. The molecule A and B are two molecules of the same gas, let us call hydrogen. Okay, so the one molecule of hydrogen, the other molecule of hydrogen, they are colliding. Let us consider an hypothetical, not hypothetical, very rare case. What is that rare case? Both these colliding hydrogen molecules are possessing same amount of energy. Okay, so let their energy be E. Okay, fine. Let their energy be E. So when they collide and after collision, they get deviated. Before collision, the energy was E. After collision, will the energy still remain E? This is our question. Actually not. Okay. Rather, what happens? Of course, we are talking about something called elastic collisions. In elastic collisions, there is energy alteration after collision. There are also something called inelastic collisions in which there is no energy alteration after collision. But we are thinking of elastic collisions now. So energy alteration takes place. So when the gas molecules after collision will no longer have same energy. So now the energies would have gained some other value, would have acquired some other value. Let us call that E1 and E2. But whatever the case, the total energy has to be same, because that is the law of thermodynamics. Energy can neither be created nor be destroyed. Even due to the collision, energy cannot be destroyed or created. Therefore, if the total energy was 2E, because the molecules were bringing E and E, the total energy is 2E. After collision, you are going to add up E1 and E2. That should still come to 2E. Okay, that is the point. But I mean, that's a different point. But what are we looking at? These two molecules now have a different energy than the previous one. And as well, now these two energies have become different. Okay, so understanding this in terms of energy is easy. Now let us let us look it from the angle of velocity. So two molecules were moving with a velocity v. After collisions, do they still move with a velocity v? Definitely not. Their velocities would get altered. Very rare case, they may still move with the same velocity. But most of the cases, their velocity gets altered. So what happens? One molecule may decrease its velocity. The other would definitely increase its velocity. Now, okay, why did I give this example? So imagine this collision and redistribution of the velocities and energies are happening across the entire sample of the gas. Millions of trillions of collisions are taking place every second. So what would happen to the velocity of individual gas molecules? Or simply, if I have to put a question like this, because of these random collisions and too many incidences of redistribution of energies, do the molecules, all molecules in this sample, now let us think all blue dots, will all blue dots possess same energy, same velocity? No, definitely not. They have different velocities now. So if I have different velocities of each molecules, now I cannot, for example, uh, I cannot, for example, ask you a question. What is the velocity of a gas molecule? You know, you cannot give a very precise answer to this question. Why? Because the velocity has now individual velocities of gas molecules keep changing, first of all, basically, because they are under constant collisions. So what is a more precise and more meaningful question? I can simply put a question. What is the average velocity of the gas? What is the average velocity of the gas? Even this question is not fully meaningful, in the sense, like even if you take air around you, example, all molecules in the air do not move at same velocity. Definitely not. Few molecules will move slowly, few molecules will very fast. On an average, what is the velocity? This question you can ask. But again, this question is not fully meaningful, in the sense, this doesn't capture the entire picture of the velocities, the complete picture of the velocity. Still, this question doesn't capture. So, instead of telling velocity of individual molecule, instead of telling average velocity of all the molecules, I would rather start a new term, tell a new term. What is that? What is the velocity distribution? Okay. What is the velocity distribution? So I'm introducing a statistical term here. What is that? Distribution. Anyways, before understanding what is distribution, let us look into one more aspect of this whole story. What is that? All the distribution velocities, all those things I can calculate for a given temperature. What happens if I increase the temperature or if we decrease the temperature? Definitely the average velocity changes. In fact, the velocities and temperature are directly proportional. So there was one website which was having this good cartoon where they just showed how the distribution varies with respect to okay, I'm sorry, I did not get that. Anyways, you can change the temperature and visualize yourself where uh, yes. Yes, sorry, yes, you can see this now. Okay, can you see this? Now let me you can see a interactive website here. Increase the temperature. What happens? Yes, see this? Now the molecules are moving fast. Now let me increase the temperature. What happens? So increase the temperature. Reset the experiment. Increase the temperature to high. Okay, let me put it at a high. And then, okay, see this? So reset the experiment. Low temperature. Slow motion of the molecules. Medium, velocity has increased. And then high, it's too fast. The molecules are moving too fast. Is it not? So after these visualizations, what is the thing which comes to our mind? Two things. One, the individual gas molecule, or okay, simple. All gas molecules do not move with same velocity. Very first observation. Very first conclusion. All molecules do not move with same velocities, same speed. So few molecules move very fast, few molecules move very slow. But average, on an average, there is an average number of molecules which move with a fixed velocity. So that's what we call velocity distribution. Now, this velocity distribution is strongly dependent on temperature. If you increase the temperature, all velocities increase, basically. Your fast moving molecules become very fast. Slow moving molecules will become fast. So usually at higher temperature, the velocities increase. Even then, even if the velocity has increased, still there is a distribution. Even at high temperatures, all molecules don't move with same velocity. Still there is a distribution. Okay. So now we will understand what is the statistical term distribution. When I'm talking about distribution, I'm talking here of velocity distribution, right? Speed distribution. Maybe this may appear a bit technical to you people, speed and velocity distribution. But the statistical term distribution is not very strange one. Now, we all go to markets to buy groceries. And onion is the most stable grocery, right? We can't cook anything without onion. It's a main ingredient of any dish, onion. So if you go to a shop, a grocery shop, and buy onion, do you think all onions would be of same size? Definitely not. All onions are of definitely not same size. You can have big onions, small onions mixed in the bag. So what would an intelligent customer like me or you do? We pick only the bigger ones usually, or the medium-sized ones, leaving behind the smaller ones. So that's a different part. The thing is that in a sample, in a gunny bag, in a sack of onions, all onions are of not same size. So you can classify the sizes, right? Small, medium, large, and extra large, XL, extra large. You can do this. So if you have classified this, what does it mean? You have pinpointed the individual sizes. Okay. But again, when you mix them, the sizes get mixed. So what do I call now? This sack of onion bag has a size distribution. Size distribution. If you are a careful observer, and if the shopkeeper is a very good friend of you, you can take a bit longer time and have a deeper look at that gunny bag. Usually what you see, even though there is size distribution, very large and very small onions would not be in relatively larger numbers. So small onions, okay, I'll switch over to Kannada here. Small onions ತುಂಬಾ ಕಮ್ಮಿ ಇರ್ತವೆ. ಅದೇ ತರ ತುಂಬಾ ಲಾರ್ಜ್ ಆನಿಯನ್ಸ್ ತುಂಬಾ ಕಮ್ಮಿ ಇರ್ತವೆ. ಜಾಸ್ತಿ ನಂಬರ್ಸ್ ಅಲ್ಲಿರುವಂತ ಆನಿಯನ್ಸ್ ಯೂಶುವಲಿ ದಿಸ್ ಮೀಡಿಯಂ ಸೈಜ್ಡ್ ಆನಿಯನ್ಸ್. Is it not? So if you now plot a graph of, okay, so now you plot a graph of number of onions against their sizes. Understanding? See, what am I telling you now? I am just making you understand the whole concept of distribution. As I told, this is a statistical parameter term. So I am making you understand, giving an examples from our real life onions. So now if you plot a graph of size of onions against number of onions with that size. So now we will take 4 sizes: small, medium, large, extra large. So put it on your x-axis. On the y-axis, you put the number. That's what I told. If you have a lot of time and a shopkeeper is a good friend of you, take a count of those onions. Small sizes, how many onions? Medium ones, how many are there? Large ones, how many? Extra large, same thing, how many are there? So now you make a graph with the values you have got from your counting. So how that graph would look like? Basically how that graph would look like. It may look like this. Of course, it's a graph of Boltzmann distribution. Anyways, don't worry. Now let us now call this graph onion size distribution. Statistics can be applied to anything. Yeah, it's not that in your college you apply, in your classes, chemistry classes, you apply that to gas molecules. Go home and apply it to onions and potatoes. Okay, statistics is a very good friend of ours. Fine. So it usually looks like this. Small onions will be here. The number of onions with small size, lesser in number. Similarly, very large size onions will also be lesser in number. Usually medium sized onions will be more in number. So if I plot a graph of number of onions against size, then that becomes a distribution curve. Hope you understood this. That becomes a distribution curve. Same thing now we have done. From onions, we will come to gas molecules. So now gas molecules, but what is the property of gas molecules we're looking at? Not the size of them, rather the velocities. Whatever you did in your onion experiment, replicate it, repeat it in your gas experiment also. Take individual gas. I mean, in the gas experiment, repeating is very difficult. Is it not? Onion, you can visualize and see the size yourself. But in gas, it's not like that. Now let us assume that you have a technology to see the individual velocities. Assume, hypothesis, assumption. Take individual gas molecules and then calculate their velocities. Number of gas molecules with velocity V1. Take the value. Number of gas molecules with velocity V2, V3, V4, where V1, V2, V3, V4 increasing in that order. Velocity is increasing in that order. So you still get a distribution curve like this. So when was this first noted by whom? It was basically in 1888, 1880s. Two scientists, Maxwell and Boltzmann, observed this and formulated a law to what? To give us the function of velocity distribution. Fine. So what does a Maxwell Boltzmann distribution law essentially is? It is a law, or it is an equation, or it is a function. They are recognized by different names. It is also called Maxwell distribution law, Maxwell distribution function, or sometimes Maxwell distribution equation. This is the equation basic. So what is the equation? What is the equation? Literally, dn by n is equal to m divided by 2 pi kb capital T to the power of half. Few equations also give this as a square root. You can remove square root and put a half as an exponential. So half e to the power of minus mv square. And remember that mv is the kinetic energy term. Minus mv square divided by, again, 2 kbt into dv. So looking at the equation, we can tell this is a differential equation because you have d by dn and you have dv terms. These are all, this is a differential equation. The differential equations, if you work with, you can in fact integrate this under different conditions and get the result of your choice, which we are going to do later anyways. So this is basic form of Maxwell distribution law. dn by n into so much. And what are the terms here? dn by n. What is the dn by n? It's the distribution now. Fraction of molecules moving with a velocity of v to v plus dv. So now, okay, what is that? Let us choose a small fraction of a small range of velocity. Okay, as I told you, no molecule will have at any instant of time pinpointed exact value of velocity. Okay, unlike the size of the onion, which is not going to vary at all. but the velocity of the gas molecule keep varying constantly. So instead of choosing a pinpointed value of V, you take a range of V. What is V? Speed or velocity of the gas molecules. V plus dV. So a small range of